software bugs are an intrinsic part of software development. There is great variation among the classes of bugs that we can find out in the field, and not all of them may be worth the same amount of our effort. My name is Christoph Reichenbach from Lund University, and I've spent much of my adult life creating bugs. In this video, I make a first dive into the world of software ticks, a class of bugs that we here define in an attempt to capture bugs that are clearly worth studying and removing. One of the places in which developers run into bugs are reports from static checkers. These tools can find and classify even bugs that the developers have never heard of. For instance, consider this user-defined iterator class in Java. This iterator will keep returning elements even when it should have finished iterating. The spot bugs checker is able to identify this bug indirectly through a specification violation. The Java standard library namely mandates that the code must throw a special exception when there are no elements left, but the caller still asks for more. This bug is an example of a defect as defined by the IEEE. It does not meet its requirements or specifications and needs to be repaired or replaced. However, not everything that a static checker reports is a bug. Here, the spot bugs checker reports that we are ignoring an exception, even though ignoring the exception is completely safe. Nor is everything that they report a defect. Here, we are cloning an immutable Java string object into an identical string. Spot bugs identifies this code as a bug and explains that this bug wastes memory. While that is clearly true, the bug did not violate any specifications of this program. So this bug was not a defect, but it was a bug in the sense that it was clearly undesirable. For software engineers and bug checker developers, this raises the question of where the line is between a real bug and a non-bug. To look for answers, we turn to the literature in this field. For example, Herzig, Just and Zeller in a 2014 study analyzed more than 7,000 bug reports in open source projects. They found that more than 33% of bug reports were not real bugs in the sense of asking for corrective maintenance. To pick two examples from two different open source projects, these two bug reports show users of the Chrome web browser asking for user interface changes that make the tool more closely reflect tools that the users are already familiar with. The Chrome development team rejected both, trading off between different needs of different communities. Disagreement on what is and is not a bug makes it challenging to understand whether tools for bug checking and bug fixing are effective. Without a clear decision criterion, we can't tell whether a given bug report is a true positive or a false positive. Consider EIExposeRep, a bug category that was among the first 50 bugs detected by the FindBugs checker. This category highlights methods that expose a reference to an array that is part of an object's internal state. The rationale behind this bug is that returning a mutable object allows untrusted callers to modify the object's internal state. However, sharing state is the norm in imperative programming. It may enable certain bugs, but it is not itself universally problematic. Instead, we can view this pattern as codifying a particular strategy for defensive programming. To satisfy this defensive programming strategy, we need to write more code, which may introduce bugs, and do more computations. The strategy may still be valuable, but we can see that this bug category is a trade-off rather than a universally undesirable code property. This makes it hard to evaluate bug reports for EIExposeRep. How can we know if we have a true positive or a false positive when we don't even know what bugs we are defending against? A 2019 study by Catalino and co-authors shed some light on bugs that are problematic but not necessarily defects. In their study, the authors surveyed 1,280 bug reports and then split them into 9 different categories. Program anomaly issues, the largest category, describe undesirable program behavior like premature termination. GUI-related issues are bugs that complicated user interaction with the program, such as requiring an unexpected program restart. Test code-related issues are issues in running and interpreting unit tests, while other categories like performance and security describe bugs that reduced software quality in certain dimensions. The authors of the study do not report which of the bugs were defects, but we can see several classes of bugs that are clearly undesirable in general. A 2014 study by Palomba and co-authors on open source and industrial developers examines bad smells, and similarly finds that some of them are generally undesirable. The developers highlighted several bad smells that they considered to be important threats, all connected to the complexity of interaction between code. Other smells, less clearly linked to complexity, they found to be much less problematic. What we've seen is that not everything that a bug checker or user calls a bug is truly a problem, not just because of false positives, but also because some bug categories can depend on context. They can serve heuristic approaches, for instance to defensive programming, or reflect the interests of a particular community at the possible expense of another. We've also seen that there are some bugs that are clearly universally problematic, whether or not they correspond to an explicit specification. Inconvenient user interfaces, premature termination, and security bugs are all problems that waste end-user time. Problems in the testing framework or the code complexity waste developer time. Performance bugs can affect both users and developers, but even when they don't, they needlessly consume memory, bandwidth, CPU time, or electricity. The common theme between these categories is that they unambiguously waste effort by humans, machines, or both. We call these bugs software ticks. They suck resources out of a software project. More concretely, we define software ticks semi-formally as follows. Given some software system, a software tick is a property of that system such that we can transform our software system into an equivalent one, that is, a system with the same behavior, that is strictly more resource efficient. As before, we mean resource efficient in the sense of machine effort and human effort. In our paper, we also describe an optional notion of scope that describes an additional knowledge about the program. If we use this scope to capture developer intent, we can use this knowledge to refine the set of ticks. Software ticks are a subclass of the class of bugs that we can consider universally undesirable. For example, a wasteful string constructor invocation increases code complexity and consumes resources. It is a tick. Conversely, exposing an internal program array representation is a heuristic with a trade-off, so it is not a tick. For any given program, ticks and defects together are a subset of the program properties that we can confidently treat as undesirable. While ticks may also be defects, the criteria of the two categories are quite distinct. Defects capture a violation of an explicit specification, while ticks capture wasted resources independently of any program specification. In other words, we characterize ticks purely by their wasteful interaction with the rest of the world. We propose ticks as a concept to help practitioners during bug triage, but mainly as a tool for researchers, especially for static analysis and bug checker researchers. For researchers, ticks gives us a straightforward way to focus effort. The outcome of removing a tick is a net positive by definition, which makes it worthwhile to explore, for any given bug definition, does it actually characterize a tick? And if not, what do we need to do in order to refine it to become a tick? Finally, ticks highlight an area of research that deserves more attention, detecting and characterizing wasted user effort. Consider the following code example. The program here takes a list of command line parameters from the user and then interprets the first parameter as the name of a file that it should read data from. After it has read the data, it processes it in a potentially lengthy computation. Then, after the computation is completed, the program interprets the second command line parameter as an output file to write the data to. Now, if the user only specified one parameter, the program crashes here with an error message that is hard to map back to the user's mistake. That means that it wastes the user's efforts twice. First, by reporting the problem long after the crash was foreseeable, and second, by not mapping the internal problem back to the user interface, so that makes it hard for the user to understand the cause of the problem. In other words, the error was neither timely nor actionable. We expect that there are similar open questions and opportunities for user interface ticks that are worth exploring from the perspective of static and dynamic program analysis. Here, we've proposed software ticks as a sharp criterion for identifying bugs that are definitely worth resolving, and thus as a focus point especially for researchers and tool developers. Software ticks are a class of bugs that are unambiguously wasteful when it comes to human and machine effort. We can thus easily make a case, as with software defects, that software ticks are worth detecting and removing. There is, however, one key difference between software ticks and software defects, and that is that software ticks need no specifications.
Yes, we're live for the fourth and final paper of this session on defect prediction and bug characterization. And I'm super happy to have Christoph Reichenbach from Lund University in the south of Sweden here with me. I'm Robert Felt. So we're quite close. It's actually like 2.5 hour train ride between us, but here we are. And this is a near paper, so very important for the health and vitality of our community and evolution, also of our field. Big thanks to Christoph for writing this paper and daring to think and question our sort of fundamental concepts of the field. So great, I look forward to this, and we already have very great feedback here. Fantastic talk, says Timothy, and I agree, it was a great video. And he asked, have you tried to find a proportion of ticks in real software that wastes different kind of resources?
I have not. It's a very interesting question, but it's one of the things that I think is really worth looking into, so that we know what we should actually be putting our research effort into.
Yeah, I guess since this is near, right? I mean, it's early days, of course.
Yes.
But, have you continued the work since you submitted, or are there any plans?
We have had some plans, but we don't have the people in place yet to do the relevant piecing together of the information that we want to do there.
Mm-hmm.
So it's.
So I had a more high-level question, maybe. So, if I consider the distinctions you try to make between different types of bugs, say, and ticks, as you define them, there seems to be also a connection between the two concepts in QA and Q&A and testing of software verification versus software validation. Have you considered your concepts in relation to those?
I have not yet, but I think it is a very interesting question. So if you look at the differences between verification and testing, then I think you are pointing exactly at the bridge there, in a way, that we're seeing at that level also. Because with verification, you assume that you know what the properties are that you are verifying against, whereas with validation, you want to know, does it actually make sense? And in a way, ticks are a mechanism or a way of describing the kinds of things that we always expect to pop up during validation. That is, the things that make sense to translate into implicit or universal verification constraints. That's how I would look at it.
Yeah, so you could use it as kind of a proto model or proto sort of nomenclature to refine the view of validation, maybe to make it a little bit more distinct.
I think that's a very interesting idea. Thank you. I'll have to think about that.
The thing that stood out to me was that okay, I mean, because if you consider validation, it's really like, what does it mean in the context of maybe not even all the end users, could even be individual end users, right?
Yes.
And then
I think that gets us into the realm of things that, given a certain context, would be a tick or would not be a tick. And most software is written with the intent for a particular context. And if you know that context, and if you can write down that context, then you may be able to get, perhaps even automatically, a far more refined version of what you expect to get during validation, and therefore what you expect to be the relevant ticks in this space.
Yep. We don't have a lot of time. It's a shame, actually. I think near papers should have more discussion time than normal papers. But I mean, maybe we can do it quickly. Maybe not. But the way you define a software tick, to me, it seems that I could also say that any bug could be a tick, but you try to describe it more as ticks being a subset of bugs, or how do you view that?
Yes, so bugs themselves, if you look at the literature, you'll find a lot of definitions that don't necessarily mean something goes wrong. They might also mean the code structure is bad, or it doesn't have a feature that I want to have. And this I would really like to clearly distinguish.
Yep. Okay, unfortunately, we have to stop there. Big thanks, Christoph.
Thank you very much. I appreciate it.
Yeah. Thank you.